Welcome to Organic Chemistry for the MCAT exam. Organic chemistry is the chemistry of carbon-based compounds. Of the 4 basic sciences that you must know for the MCAT exam, organic chemistry is the subject that you need to memorize the least amount of information. The reason for this is that organic chemistry is based on certain basic rules. Once you've memorized those rules and you've understood those rules, then the rest is just play. First, let's learn some definitions. Composition. Composition refers to the molecular formula. Constitution refers to the order and kinds of bonds. Isomerism are different compounds with the same composition. For example, let's look at C4H8. C4H8. We can look at this particular compound. Now note, this is C4H8. 1, 2, 3, 4 carbons. Number of hydrogens, 3, and 3, 6. 2 more here, that's 8 hydrogens. So this is one way that we can look at a compound which has the molecular formula C4H8. Let's look at another compound. CH3, CH, we have a double bond here, CH3. So here we have 4 carbons, 1, 2, 3, 4 carbons, 3 hydrogens, 4, 5 hydrogens, another 3, 8 hydrogens. 2 different compounds, same molecular formula, same composition. Therefore, these are isomers. C4H8 can also be represented by certain geometric figures. For example, this looks just like a box, but the routine in organic chemistry is that every corner of a geometric figure represents a carbon. Then you just need to keep in mind from your general chemistry that carbon bonds 4 times. Carbon has 4 valence shell electrons available for bonding, and therefore it can bond 4 times. So to begin with, we have 1, 2, 3, 4 carbons. Then we have to put in our mind that because carbon is bonded 4 times, we have to add in our minds a hydrogen to make it such that each carbon is bonded 4 times. For example, at this corner here, carbon would be bonded to another carbon up there and another carbon over here. So then clearly this carbon must be bonded to 2 other hydrogens that are not noted. And in fact, that's the way it is in organic chemistry. Sometimes with geometric figures, the hydrogens will not be noted because they're implied. No other atoms are implied, only the hydrogens. So that if you see that carbon is bonded to 2 twice here, therefore there must be 2 hydrogens here, 2 hydrogens here, 2 hydrogens here, and 2 here. Therefore we have 1, 2, 3, 4 carbons, and we have 2, 4, 6, 8 hydrogens. So here is a third way of representing a compound, separate compounds with the same molecular formula or the same composition, C4H8. And here's another one. So here we have a triangle. Once again, 1, 2, 3 carbons must be in the triangle because each corner of the geometric figure. Then we have 3 carbons here and then the 4th one there. So we have our C4. Then in terms of H8, well, clearly there must be 2 hydrogens here at this corner because there's only 2 bonds for this carbon. 2 hydrogens here, so we have 4 hydrogens. 3 here, 7 hydrogens. Over here, the carbon is bonded once to another carbon, once to a carbon here, once to a carbon there. That's 3 times it's bonded. Therefore, there must be 1 hydrogen bonded to this carbon. So that makes C4H8. So once again, we've looked at 4 different ways, different compounds with the same composition, the same molecular formula. Therefore, these are all different types of isomers. Our next definition is that of conformation. Conformation is the shape due to free rotation about sigma bonds. You may remember from your general chemistry review that sigma bonds are single bonds. So let's look at this substance, this organic chemical, and it has 2 carbons. Therefore, its name starts with eth, since 1 carbon starts with meth, 2 with eth, 3 with prop, 4 with bute, 5 pent. So this starts with eth because there's 2 carbons, and it's an alkane because it's a simple hydrocarbon. And it's fully saturated, which meaning the carbon is bonded to the maximum number of different atoms as possible. In other words, there are no multiple bonds. So this is ethane. And in this compound ethane, what we're talking about is that the single bond between the carbons, there is a free rotation. There is turning. If you can imagine an axle between wheels, and the wheels can turn independently, that is conformation. So there's free rotation about this single bond. Now there's many ways to represent this free rotation. One is called a Sawhorse projection. In a Sawhorse projection, we have, say, our carbon here, and this carbon would be this one. I'll be representing over here. We'll have hydrogen up here. We'll have another hydrogen that looks like that. Another hydrogen coming out sort of in a triangle shape like this. Now, this hydrogen is going to be representing this one, this hydrogen, this one, this hydrogen over here. Then we go back. This is our bond between the carbons. We have another carbon here, a hydrogen here. Then we have a bond here to a hydrogen. Then we have this sort of triangle shape again, bonded to another hydrogen. Now, the routine here is that when we see a broken line in organic chemistry, it means this hydrogen is going into the plane. And this solid triangle means this hydrogen is coming out. Because though we write these sort of sticks and lines and so on, the truth is these are 3-dimensional molecules. And that because carbon is bonded to 4 different atoms, we know that carbon must be in the center of a tetrahedron. And a tetrahedron is sort of shaped like a pyramid, in which, so you have the carbon here, you have a hydrogen above it, and then you have this triangle as a base, in which there's a hydrogen towards you, there's a hydrogen away from you but off to the side, and then another hydrogen away from you but off to the side. So if we have this tetrahedron represented here, where the line is in the plane, this broken line means that it's going away from you. This one is coming towards you. Then we have back here another CH3 group, CH3, a CH3 group because C is just 1 carbon. That means it's a meth. And then it can't end in ane because an alkane would be CH4, it would be fully saturated. This is CH3. Whenever you have an alkane minus 1 hydrogen, it ends in -il. So then we have a methyl group back here, CH3 group. And so we see that Here as well, the hydrogen goes into the plane, this hydrogen comes out of the plane, and so we have our three-dimensional image of the molecule. Now when we look at this Sawhorse projection of the ethane molecule, note that if I'm looking at the molecule from this angle, then for me, this hydrogen would be in front of this hydrogen. This hydrogen would be in front of this hydrogen, and this hydrogen would be in front of this one. Because this hydrogen is in front of that hydrogen, we say that it eclipses this hydrogen. So this is called an eclipsed conformation. There is yet again another way that we can look at this eclipsed conformation. And that is, if I were to be looking at it just like this, sort of head on, like this, at this angle, what I would see is I would see this carbon, but I wouldn't see the carbon behind it. I would see this hydrogen, but I wouldn't see the hydrogen. And so we can come up with something called a Newman projection. And in the Newman projection, which is drawn like this, we would have the carbon in the middle, then we would have a hydrogen up here, we would have another hydrogen here, and we'd have another hydrogen there. So this is as if I'm looking at it from this particular angle. I can't see the hydrogen in behind, and I can't see the hydrogen behind that one. This is an eclipsed conformation. So this one is eclipsed. Now the idea behind conformation is that there's free rotation about the sigma bond or the single bond. Therefore, let's keep this CH3 group the same in its same conformation. Let's spin the one behind it around and see what would happen. Well, if we were to just spin this one around, well, we would have basically the same thing in front, which is broken line here, and then we have the solid triangle here of a hydrogen. Then we have the bond going in behind, as this one does. But now we're going to spin this. Okay, so then we're going to have carbon here, but then we're going to have one bond going up this way. We'll have a hydrogen which has been spun around, and then this will go this way, and then we'll have another one going from below. In other words, it's the same molecule as this one, same CH3 group as here, but this one has been spun around. This one has been twisted. So it's been twisted around, and so if we were to look at a Newman projection of this as it's been twisted around, well, if I'm looking at it from this angle, I will see hydrogens off to the sides, because the hydrogen that was just in behind, now by twisting this, I can actually see it off to the side. So the Newman projection here would be something like this. We'd have the one in front, the hydrogen in front. We'd have this hydrogen in front and this hydrogen in front. But this is the CH3 group in front. That hasn't changed from this. But the CH3 group in the behind has changed. So now we're going to see off to the sides, we're going to see some hydrogens. And this is called, because it's sort of twisted, it's turned off to the side, this is called a staggered conformation. So this is staggered. Now, in terms of room temperature, these molecules at room temperature, some might ask, well, what do you have? Which one do you have preferentially or often or whatever? And most organic chemistry, more than 90% of organic chemistry for the MCAT exam, comes down to basic electronics, meaning opposites attract and like charges repel. 90% of organic chemistry will come down to those types of basic concepts. And so, based on that knowledge, that opposites attract and like charges repel, keeping in mind that around these hydrogens would be a shell of electrons. And because there are electrons in these shells, there will be a repulsion between these electrons. So there's electron shell repulsion. Because electrons are negatively charged, they're the same charges, so they want to be as far apart as possible. So these hydrogens, one is behind the other. Now they're a certain distance apart, but they're behind each other. They would like to be as maximally apart as possible. So if this twists, therefore, one would not be right behind the other. It'll be behind, but then at an angle. And therefore, it would be maximally apart. Therefore, the staggered conformation, as it twists, where you get the hydrogens off to the sides, this would be a situation that they would be maximally apart. Therefore, a staggered conformation is more stable than an eclipsed conformation. However, at room temperature, which they can always try to apply as a trick in the exam, do you get eclipsed conformation? Most definitely, because the definition of conformation is that there is free rotation about the single bond, or the sigma bond. And because there's free rotation, there's continual movement at room temperature along this bond. And so it is important to keep in mind that yes, you do get changes of all the different conformations between eclipsed and staggered, including eclipsed and staggered conformations. And you get all of these movements at room temperature. However, at any given moment, most molecules will be in a state which is staggered or similar to it, because most molecules will tend towards the more stable conformation, but all the different other conformations are still possible. Our next definition is that of configuration. Configuration refers to the permanent three-dimensional shape of a molecule. For example, let us look at this particular molecule. First, we'll name it. There are 1, 2, 3, 4 carbons. Therefore, it must start with bute. There is a double bond. Therefore, it is an alkene because it's the hydrocarbon with the double bond. Therefore, this must be butene. In order to be precise, we need to name the carbon where the double bond is attached to. So this would be the first carbon, because we can name any carbon in the link starting with the lowest number, which would be attached to the double bond. So here we have 1, 2, 3, 4 carbons. 1, 2. At the second carbon, there is a double bond. Therefore, this substance is called 2-butene. Now, as we're looking at 2-butene, we see the triangular shape, suggesting that this CH3 group or methyl group is projecting out of the plane. This hydrogen is out of the plane, and this methyl group is into the plane, and this hydrogen is into the plane. Each carbon would be at the center of a triangular shape. You may remember from general chemistry that that means there is an sp2 hybrid bond, meaning there is one sigma bond, and there is a p to p bond, which means there is one pi bond. So this is the molecule. Now note that this methyl group and this methyl group are on opposite sides of this double bond. When we have the main substituents meaning the attached group at a particular functional group. So when we have the main substituents, also called ligands, that are attached to a particular area, when they're on opposite sides of a double bond, we call this trans. So this is trans configuration. Now we're going to look at a substance which has the identical molecular formula. So here we have the same molecular formula. This is indeed 2-butene. Now this time the two methyl groups are on the same side, so they are the substituents. Why? Because once again hydrogen presents barely any importance. Just like when we look at geometric figures, we have to add the hydrogens. Sometimes they're not even written in. Well, so we're not looking at hydrogens as substituents or ligands, but these methyl groups certainly would be regarded as substituents. Both of them are on the same side of the double bond. They're not on opposite sides of the double bond. This configuration is called Cis configuration. So to be precise, this compound is called cis-2-butene, while the other is called trans-2-butene. Now, in terms of stability, which of these molecules would be more stable? Well, once again, it comes down to electronics, and here's CH3, which you have to try to imagine in 3 dimensions. There is a ligand here. It's a group. There's a group here. And here, there's just little hydrogens. And of course, hydrogens are, well, it's the smallest atom on the periodic table. And so we have this small atom here, but we have this large group here, a large group here. And on the outer surface of these groups are electrons. And therefore, these electrons want to be as far apart as possible. So if you have 2 large groups here, obviously there's going to be some electron shell repulsion in the cis configuration. Then when we look at the trans configuration, where we have a large group here, the other large group is way on the other side of the molecule. And so they're maximally apart. Therefore, the trans configuration is more stable. Now, do you get a twisting and turning along this double bond so that you can go from this trans configuration to the cis configuration? Because if you twisted this, brought the CH3 group down, then you would have the cis configuration. Does this occur at room temperature? Absolutely not. Because to go from the trans to the cis, because there is a double bond, and the double bond restricts, in fact, it prevents free rotation. By having the double bond, it prevents free rotation about this bond, and therefore you cannot go from the trans form to the cis form without a chemical reaction. It's not something that occurs spontaneously. So trans-2-butene and cis-2-butene are independent and have different properties because of the fact that they do have the same composition, but the way that the molecule arranged is different, and therefore these are 2 isomers. The fun in organic chemistry can be found in the reaction mechanisms, and that is to look at the way different organic chemicals interact. And in order to do that, we need to continue with our definitions. Our next definition is that of a nucleophile. A nucleophile is nucleus-loving. That is literally what the word means. So a nucleophile is a substance which is attracted to the carbon nucleus. Of course, a nucleus is composed of protons and neutrons, and therefore a nucleus has a positive charge. So something that is a nucleophile must be in itself either negatively charged or partially negatively charged. There are electrophiles, which is obviously the opposite, because an electrophile would be electron-loving. It is something that is attracted to electrons, and therefore in itself it must be positively charged or partially positively charged. Then there are leaving groups, and leaving groups are substances that are bumped from the carbon nucleus. So that's the best definition or clearest definition that I could provide, but it would be even more clearer by looking at some examples. Now let's work out this particular reaction. First, we'll name the compounds. So here clearly we have sodium, and here, well, a common thing in organic chemistry is that when you see a compound that you're not familiar with, think about compounds that you do know that are very similar, and then it will help you to understand the properties and even the naming of these compounds quite often. For example, if you've never seen this compound before and you don't know how to name it, well, consider the following. if this compound was this compound, you would know what to say. This is sodium hydroxide. It's a very famous compound, of course, in both organic and inorganic chemistry. Sodium hydroxide. So now, if we were to look at this substance, we have sodium, and we have this, and oxide. So this is sodium hydroxide. This is sodium, and this is CH3. CH3 is the methyl group. So this is sodium methoxide. So this is how we name the compound, sodium methoxide. And over here, well, again, this is the methyl group. So you can call this methyl iodide, or you can call the compound iodomethane. Either way, it represents the same compound. So, in solution, what would happen if these two compounds were added together? Even if you had no organic chemistry experience, you should be able to work out the result of this reaction. You may want to take a moment and pause and work out the product, or we'll work on it together. So, if this is in solution, the first thing that you would consider is that thinking of what would happen with NaOH in solution. Well, we would get Na plus OH minus. It would dissolve in solution and produce Na plus and OH minus. Similarly, if you have sodium methoxide in solution, we would get Na plus and OCH3 minus. So that's how we start. We're going to begin our reaction mechanisms by identifying the compounds and then starting to work on the electronics, because that is the basis for the reaction. It's going to be opposites attract, like charges repel. It's the same old, same old. We're going to have different words for these types of things, but it's always going to be based on the same basic principles. So here, in terms of working out the electronics, all we have to do is look at the periodic table, which again will be provided to you on the MCAT exam. So you look on the periodic table knowing that iodine is bonded to carbon. Since carbon is bonded 4 times, so it's bonded 3 times to 3 different hydrogens and once to iodine. And so in the bond between carbon and iodine, how are the electrons shared? Well, you look at the periodic table, remembering that as from basic general chemistry, as you go to the right along the periodic table, you have an increase in electronegativity. And therefore, carbon is to the left, iodine is to the right on the periodic table, and therefore iodine has more electronegativity, meaning that when the atom is in a molecular environment, it has a greater pull on electrons. So iodine is going to be a little bit negatively charged because it's pulling electrons to itself. The symbol for a little bit negative is delta negative. Therefore, this carbon is going to be delta positive. This is very common arrangement in organic chemistry, that we get a delta positive carbon, because often, not always, but often carbon is bonded to atoms that are more electronegative. And this you would be able to determine based on the periodic table. So here we have delta negative and delta positive. Now, in order for you to make this reaction work out without any experience in organic chemistry, you need to know one more point. And that is the definition of a spectator ion. A spectator ion are ions that are found in the first and second group of the periodic table, with sodium and potassium and calcium and magnesium and so on. These are ions that are found in the first and second group of the periodic table that when they're involved in organic chemistry reactions, they're spectators. Meaning that when the reaction is occurring, they're just going to observe. They don't get involved in the nitty-gritty. And so at the end of the reaction, when everything is finished, then that particular ion will associate with whatever might be left over. But it does not actively get involved in the reaction. So when we look at this, we have one spectator ion, which is the sodium, since it is in the first group of the periodic table. So once we know that sodium is a spectator ion, and we can just block that out of our minds for now, then when you observe the reaction, there's only one thing that can occur. After all, this is negatively charged. Has a partial positive charge, that has a partial negative charge. So the only thing in terms of opposites attracting would be this negative charge going to this partially positive charge. So then we have this negative charge, opposite attract, being attracted here to the positive charge. Why is this delta positive? Because the electrons have been pulled to the iodine, making the impact of the carbon nucleus more apparent. And therefore, this negative charge is attracted to the carbon nucleus. Therefore, this substance is indeed a nucleophile. So that's our first definition was that of a nucleophile. So the first thing that happens in this reaction is that the nucleophile is going to attack the carbon, attract it to the carbon. And so in organic chemistry, the routine is that when you show an arrow, the arrow represents, when you're doing reactions, it represents the flow of electrons. In other words, really, technically, you don't show an arrow going from something positive to something negative. You show the electrons, the something negative or partially negative, going and attacking that which is positive. That's the routine. And so whenever you see an arrow like this, it means that we have an electron pair that is going to attack a particular atom. So this is the carbon nucleus. So here, this nucleophile comes in, it attacks the carbon. However, carbon can only be bonded 4 times. We know that because carbon has 4 valence shell electrons. It can have a maximum of being bonded to 4 different atoms, maximum. So if this oxygen were to come in here and to bond to this carbon, and so it would have 4 bonds, well, it would have 5, so it would have to kick something out. So it would break the weakest bond. Now, the carbon-hydrogen bonds are bonds that are pretty much equally shared, meaning the electronegativity difference between carbon and hydrogen is very low. But the electronegativity difference between carbon and iodine is so great that it is a polarized bond, where iodine is delta negative and carbon is delta positive. Because it's a polarized bond, because iodine is drawing electrons to itself, it means of the 4 bonds to carbon, the weakest bond would be that which is polarized between carbon and iodine. So when this comes in to bond with carbon, carbon must break a bond somewhere if it wants to bond with this new substance. And so indeed it could break a bond quite easily because it has a polarized bond. It has a bond in which iodine is dying to have as many electrons as possible. So as this comes in and knocks this carbon, this is going to leave. And that is our definition of a leaving group, is a substance which is bumped from the carbon nucleus. So as this comes in, it bumps out the iodine so that the carbon could be bonded only 4 times. So what are we left with? Well, we're left with CH3 bonded to the oxygen, which was bonded to the CH3. So this would be our organic product, our product containing carbon. Then we have iodine, which is floating around in solution, I-, because it withdrew electrons to itself, so it became I- floating in solution. And then now our spectator ion, which hasn't been involved in the reaction, floats around and starts to associate with the iodine via sort of ionic bonding because of the opposites attracting. But the sodium was not actively involved in the reaction in any sense of the word. So let's look at our organic product and name it. Anytime we have an alkyl group is an alkane, meaning a hydrocarbon minus 1 hydrogen. So this is not CH4, which would be methane. It's CH3, so it's methyl. So in general, we call these alkyl groups. So an alkyl group on one side, an alkyl group on the other, oxygen in the middle. That is the definition of an ether. And so this particular ether has a methyl on each side, so it's called dimethyl ether. If it had a methyl group on one side and an ethyl group on the other, you can call it methyl ethyl ether. So this is one of the ways that you can name ether compounds. So we just created an ether with this organic reaction, looking in particular at nucleophiles, leaving groups, and spectator ions. And also keeping in mind that when you look at a compound and you're not familiar with it, consider compounds that you are familiar with and see if you can make some relation there. We've seen the basics. Now let's look at some good appropriate groups that would represent good nucleophiles and leaving groups. So good nucleophiles, one of the great nucleophiles that you'll see over and over again in organic chemistry is the OH- group, the hydroxide anion. Other good nucleophiles include the cyano anion, that's carbon and nitrogen. There is also NH2-. There is NH3, which is ammonia. Ammonia, of course, would not be as strong as NH2 because NH2- has a formal negative charge. Therefore, as a nucleophile, something that's attracted to a carbon nucleus, which is delta positive, you want to have something as negative as possible. But nonetheless, NH3 is still a reasonably good nucleophile, but NH2- would be stronger because it has a formal negative charge, whereas in NH3, the nitrogen would just have a partial negative charge because nitrogen is to the right of hydrogen in the periodic table. Nitrogen, of course, has a lone pair of electrons, a free lone pair of electrons. So these are a few. Of course, if you have OH-, one would expect that you would have SH- because sulfur is just under oxygen in the periodic table and therefore has similar properties. There's also OR-, where R represents alkyl groups. For example, we just saw the example of sodium methoxide, and so the methyl group was in this particular position. So any OR- group would be a good nucleophile. So these are examples of good nucleophiles, and in terms of some examples of some good leaving groups, well, I think better than just looking at examples of good leaving groups is to look at what the trend is. For example, let's look at a halide like chloride. So we have chloride. Chloride is a halide. That means a halogen, which is the anion of that particular halogen, and halogens can be found in the 7th group of the periodic table. And so we have Cl- here. It is a much greater leaving group than OH-. OH- is not a good leaving group, which is indeed a much greater leaving group than CH3-. CH3-, which is a methyl group, essentially. This would be a horrible leaving group, And so, and the reason that we can look at this and look at the trends is that in general, the trends of where we find a good or poor leaving group is based on the acidity. Meaning, if we were to add a hydrogen to these substances and we were to examine how acidic would that substance be, well, that would give us our trend in leaving groups. For example, if we add a hydrogen here, we have HCl. That's hydrochloric acid. This is water, and this would be methane, CH4. Clearly, HCl is a far greater acid than water is. Water is obviously not a great acid. It's neutral. And so HCl, however, is a very good acid. And therefore, HCl producing the chloride anion, it is a very good leaving group. Water, it's easier to take a hydrogen out of water because, of course, there is a water dissociation constant. There is some hydrogen cations being liberated. So it is possible, but it's just much less than HCl. It's barely comparable. But then CH4, it's even more difficult to remove a hydrogen from CH4 because it produces a very unstable anion, meaning CH3 minus. So this is very, very unlikely. And so the general trend of acidity helps us to know what would be good leaving groups. Obviously, therefore, you can be presented with a substance as a leaving group that perhaps you haven't seen very often, but you would be expected to know that it would be a good leaving group. For example, HSO4. You would expect HSO4 to be a great leaving group. Why? Because H2SO4 is a strong acid. That is, sulfuric acid is a strong acid. Here's another chemical reaction, and if you feel inclined to, you can pause here and try to come up with the product of this particular reaction, and then you can come back and we'll work it out. Now, if you look at this particular chemical, this kind of chemical is called an aldehyde. The reason it's called an aldehyde is because it has carbon double bonded to oxygen. The carbon is also bonded to a hydrogen. This configuration, no matter if this is a hydrogen or an R group up here, that is called an aldehyde. Usually for organic chemistry for the MCAT exam, there are very few trivial names that you need to memorize. This happens to be one of them because this is a very famous compound. This is called formaldehyde. So it's an aldehyde called formaldehyde, and that's because it has two hydrogens which are attached to the carbon, which is attached to the oxygen. This is formaldehyde. This particular chemical, well, its name is a little bit easier to remember. It's of course you don't have to memorize it because it's not a trivial name. You can work it out, and this is methyl lithium. So we have methyl lithium and formaldehyde in a chemical reaction. So we start, as we do with all of the reactions, which is to assign the charges. So carbon and oxygen. Oxygen is to the right of carbon on the periodic table. Therefore, by definition, oxygen has more electronegativity. It attracts electrons to itself. Therefore, the oxygen will be a little bit negative, delta negative. The carbon will be delta positive. Over here, we have a CH3 group with lithium. Lithium is to the left of carbon on the periodic table. So lithium will be delta positive, and carbon is to the right in the periodic table. So carbon will be delta negative. Now, it's not often that carbon is delta negative. This is not common, in other words. And so it happens with alkyl lithiums that we get delta negative carbons, and not for any magical reason. It's simply because lithium is to the left on the periodic table. But there is another group of substances that can produce delta negative carbons. And why is this so special? Because a delta negative carbon can produce a carbon-carbon bond. Because usually carbon is delta positive, as in this example. And so if carbon is usually delta positive, if you can produce a delta negative carbon, then you can have a delta positive carbon being attracted to a delta negative carbon, or vice versa, and therefore you can get a carbon-carbon bond. And because carbon is the basis of organic chemistry, it is a very useful thing to be able to create bonds between carbons. So this happens with alkyl lithiums, and it also happens in a group of compounds which, instead of symbolized with lithium, consider that lithium is in the first group in the periodic table. So then lithium has an oxidation number of +1. Well, if you look in the periodic table, magnesium is in the second group of the periodic table. It has an oxidation number of +2. But if you put an X group, now in organic chemistry, X is a symbol for halides, meaning chloride, bromide, etc. So it's a symbol for the halides, which are the groups in the compounds in the seventh group in the periodic table. So in the seventh group in the periodic table, their oxidation number is -1. So magnesium +2, halide -1, overall oxidation number of +1, which is exactly like lithium, which is +1. So if we were to have an R group here, So any kind of alkyl group, for example, methyl group or ethyl group or propyl or whatever, MgX, this would indeed create delta positive here and a delta negative carbon nucleus. So therefore, this delta negative would be attracted to something which is delta positive. So you can create carbon-carbon bonds. This type of substance or reagent, is called a Grignard reagent. Grignard reagent. And that is simply that we have a magnesium and a halide attached to some kind of alkyl group, and therefore it generates a delta negative carbon in the same way that this lithium generated a delta negative carbon here. So back to our reaction. We have a delta negative here. Now, remembering that opposites attract. Also, remembering that a spectator ion are the ions found in the first and second group in the periodic table. So once we know that opposites attract and that there exist spectator ions, we know that this lithium, being in the first group of the periodic table, is not going to be actively engaged in a chemical reaction. So we block out the lithium. Well, we're only left with one possible reaction, and that is that the delta negative carbon is attracted to the delta positive carbon over there. It's the only possibility because these opposites attract. So then we have this carbon becoming the nucleophile. So this is the first step in the reaction. The first step in the reaction. So this carbon becomes the nucleophile, comes in, hits this carbon. Once again, this carbon can only be bonded to 4 different things. So if something else is coming in and bonding to it, one of these bonds must break. Which one? The weakest bond. Again, the carbon-hydrogen bond is pretty much equally shared. That's not going to break. This is not going to break. So definitely it's going to be in here. And the weakest of all these bonds is the pi bond in the double bond. That's the weakest. Because in general chemistry, we discussed that having multiple bonds will create a situation which is stronger than just having a single bond. However, the strongest of the bonds in multiple bonds is the first bond, the sigma bond. The bond between the p and the p orbitals, called a pi bond, between p and p is the pi bond. That bond would be the weakest of the bonds. So therefore, of these 4 bonds, when this carbon comes in and bonds to this carbon, the weakest bond would break, which would be the pi bond. So that breaks, and this electron pair comes out here. Therefore, we have CH3 bonded to this group here, which is CH2, which is bonded to oxygen. Then we have electron pair, which has been popped out. In other words, rewriting it, we have CH3, CH2O minus. So that would be the reaction. CH3 coming in here, bonded to the CH2, which is bonded to one oxygen. The electrons pop out here. And then we have, of course, lithium just floating in solution. So lithium will be floating in solution, and therefore there's the ionic bond, the relationship between these substances. So this would be the product. In terms of naming the product, very easy. Because after all, how would you name this product? You would call this a lithium hydroxide. So here we have lithium. This is the ethyl group. So we have lithium eth oxide. So this is lithium ethoxide. And that is the organic product of this particular reaction. Now let us look closer at the carbonyl group, which is this particular group, because it is so central to many reactions in organic chemistry. So what is so special about the carbonyl group? Well, there are many things. To begin with, we've seen that this is a polarized bond, meaning that the carbon, because of where it is placed on the periodic table, is delta positive and the oxygen is delta negative. So it is a polarized bond. Also, we've seen that there is a sigma and a pi bond. There's a double bond, and they have different strengths in that double bond. We also know that because the oxygen wants to have electrons to itself, therefore we can draw resonance structures for this particular compound in which we have carbon with the oxygen negatively charged, meaning the oxygen pulled electrons to itself. Of course, if you have a neutral compound overall, if the oxygen pulls electrons to itself, pulls an electron pair to itself, well, therefore, the carbon will be deficient in an electron pair. It would have lost electrons to the oxygen, and therefore the carbon would be positively charged. So here are two different ways that you can represent the carbonyl group, and these would be called resonance structures. When you can draw resonance structures for a compound, it means the compound has increased stability. So this is a stable compound. It's a stable bond. It's a stable, what we call functional group. And we call this functional group because a functional group somehow gives us information about what kind of reactions would be involved in that particular compound. The functional group is where the action is. In fact, quite commonly on the MCAT exam, they'll put this gigantic molecule in one of their passages, which is going to frighten off people who are not too comfortable with organic chemistry. But usually, the problem is a joke, because what they'll do is they'll put in a few functional groups, like the carbonyl group being the main functional group found in organic chemistry, and because they will have a few functional groups, that's where the action will be. That's where the reactions will be occurring. And that you don't have to be as involved or see the importance as the things that are in between the functional groups. That's not as important as the functional groups themselves. So in terms of the importance of the carbonyl group as a functional group, there's the resonance, the polarization of the bond, and the stability. And because of all this, because this is a delta positive carbon, this is a very reactive site. Now we're going to look at the impact that chemicals can have by having groups attached to the carbonyl group. Let us look at this problem. The question is, which of these compounds would react fastest with NaCN? If you look at this particular compound, because there is a carbonyl group here, our functional group, there's a hydrogen on one side, an alkyl group on the other, this compound is called an aldehyde. Here we have two alkyl groups on either side of the carbonyl group. Therefore, because there's an R, C double bond O, R group on the other side, by definition, this group is called a ketone. So we have an aldehyde and a ketone. Which reacts fastest with NaCN? Well, first we'll need to remind ourselves is what type of reaction would occur. We would say that the carbon, immediately we'd say that the carbon here would be delta positive, the oxygen would be delta negative, and we would have the same thing here, delta positive, delta negative. NaCN, if you're not familiar with this particular compound, you consider compounds that you are familiar with, like NaOH, which is similar in structure of this compound. And so we know that in solution, this would become Na plus and Cn minus. Then we know that Na, sodium, would be a spectator ion. So it would just observe the reaction and associate with something at the end of the reaction. So we have Cn minus as being on our list of good nucleophiles. And plus, even if we didn't know that, we would know that it would be attracted to the carbon nucleus because there's no other choice. Sodium is out of the equation until the end, so we only have the negative charge. So this would be attracted to something positive. Clearly, the Cn minus would be attracted to the delta positive carbons. As an example of the reaction, the Cn minus would come down here. It would hit this carbon, bonding to the carbon, and then it would have to break the weakest bond. The weakest of all these bonds would be the pi bond, so the pi electrons would pop up to the oxygen. Therefore, the carbon would indeed have only 4 bonds. So this would be the expected reaction either here, and we'd expect the same reaction in here. So in terms of which would occur faster, well, we would have to consider, well, what is the difference between these two chemicals? The only difference is that this hydrogen is replaced with a CH3 group or methyl group. So how will that alter the speed of the reaction? Well, hydrogen is just a proton. So we have to imagine that this is a very small attachment to the carbon. I don't want to call it a substituent because really CH3 group is a substituent. Hydrogen is a small proton with its shell, its outer shell, but its outer shell relative to any other atom is going to be clearly the smallest. So it is going to be this small thing attached to this carbon, whereas CH3 group is going to be as big as the other side. So we have this CH3 group which has a certain size around the carbon. Now the Cn minus has to get access to this delta positive carbon in order to bond. Clearly the access route is easier here because the hydrogen is so small than to get in here where there will be these two bulkier groups. So the faster reaction would be with the aldehyde as opposed to the ketone. Furthermore, this idea that this bulkiness has an effect that will slow down a reaction, we call that effect of bulkiness of a molecule steric hindrance. So that's because this bulk effect hinders the nucleophile from coming in, so we call that steric hindrance. But the truth about steric hindrance is that sure, we call it a bulk effect and so on, but it still comes down to the basics of organic chemistry. This bulk effect is really based on the fact that on the outer part of these substituents are electrons. And here is a substance which is indeed negatively charged. So not only does it have electrons in its outer part, but it is net negatively charged. And it is attracted to the carbon nucleus, but there are these electrons around here, which is going to impede the access to the carbon nucleus.